All right. Lecture 6. Let's just jump right in. We're not going to read any of this stuff. I just want to see what the problem is, and then we're going to talk about it in natural language. Some limb is the next theorem we want to prove. Here's the situation. As soon as this loads, well, I can tell you what it is without waiting for it to load. Let's go right to here. Can we see both at the same time? I think we can. Okay, great. So, theorem. The theorem is called sum lim, which says what happens to limits as you sum them. Okay, so our assumptions are that a sequence an goes to L and that a sequence bn goes to M, right? You see that this hypothesis is called HA, this hypothesis is called HB. And we have another assumption that Cn is always equal to An plus Bn. So we have a new sequence, Cn, which is the sum of An and Bn. That's called the hypothesis on CHC. And our goal is to prove that Cn converges to, well, what should the sum of two sequences converge to, if there's any justice in this world? The sum of the limits, okay? L plus M. All right, that's our goal. Let's start the proof. Let's try this. Let's see if we can come up with a proof in natural language. So we have to prove that there's a limit. Step one. Sure. Let epsilon be given, exactly. Let epsilon be given and assume that epsilon is positive. Okay, do you see the goal state in your mind? We have to demonstrate that there exists some n. How are we going to get that n? Where are we going to get that n? So, problem, where is n supposed to come from? Supposed to come from. Guess I don't want to close it just yet. Jeffrey.
Comes from the values for an.
Right. So let's think about this. We have an. An is doing something. It's getting closer and closer to L. And then we have, so that was an. And then we have bn. And bn is doing something else. And it's getting closer and closer to M. Okay, so this is bn. And the other one was an. And then we have the sum of these two. I don't know where L plus M is. So here's L plus M. Whoops. A little too far up, huh? L plus M. And it's doing something. And the claim is that that's what we're approaching. So how do we get within L plus M of an plus bn? And we've seen this trick already previously, other than Jeffrey. Jeffrey's got an idea. Sean's got an idea. Suhas.
You you can find a big N such that all n greater than equal to big N is like within epsilon over 2 of an, epsilon over 2 of bn.
Yes.
I think like some of those something than that.
I like it. Yeah, very good. Idea, get an, in other words, go so far out so that an is within epsilon over 2 of L and bn is within epsilon over 2 of M. And once you do those two things, then Cn, which of course is an plus bn, will be, we have to prove this, within epsilon of L plus M. Okay, so that's the kind of idea for where the proof is going to come in. So of course, epsilon over 2 is positive. Of course, epsilon over 2 is positive. So HA applied to epsilon and epsilon over 2. I'm sort of mixing the formal and informal. So HA applied to epsilon and epsilon over 2 says what? Bless you. Daniel. Yep. let me be a little pedantic and call this N1 or something. There exists an N1 so that for all little n greater than this N1, perfect, less than epsilon over 2. Similarly, HB, whoops, what did I say here? Epsilon over 2, that's nonsense. Right, epsilon over 2, and then this H epsilon 2, and then H epsilon 2 says that. And similarly, HB applied to epsilon over 2, and then the same H epsilon 2 says that there exists an N2, yada, yada. Okay, with Bn and M, and still bounded by epsilon over 2. So what can we do? We know that those things exist. Akil.
We have to use n that is greater than or equal to like both of them.
We know that those N1 and N2 exist. Let's choose them. So choose an N1 and choose an N2. Okay, so now we have them. And now we are proposing something. So use N equals what? John? The max, okay? The max is the natural thing to do. But if we use the max, then I have to tell you how to deal with maxes formally. So let's not use the max. Let's be crude. Just add them. Just add them. So you're absolutely right. The max is the right thing to do. We're not going to do the right thing, but we'll do something that's good enough. We'll just add them. N1 plus N2. Then, okay, so that's our capital N. What's our new goal? Current goal. At this point, Jeffrey knows, Akil knows, John knows. Sean?
Like our current goal would be, there exists big N such that for all n greater than, or do you mean like the goal statement itself, or?
Yeah, what's the current goal?
Oh, we use it, sorry.
Because we use the big N. Beautiful.
Absolute value of Cn minus L plus M is less than epsilon.
Perfect. Okay, so I'm just reminding you, I'm just anchoring the goal state that we don't see when we write formally, when we write informally in natural language. Okay, so that's what we have to do. So what's our next step? Akil. Yeah, let little n be given, and assume that little n is greater than or equal to N1 plus N2. In particular, little n is bigger than N1. So we have, let's call this HN1 is that, or maybe HN1 is what I would call this hypothesis. So maybe let's call this, let's just call it, I don't know, F1. Yeah, F1, fact 1. Fact 1 is that N1 is less than or equal to N. And this is bound by bound. And we have F2, which is that N2 is less than or equal to N, also by bound. Bless you. Okay, so this choose N1, and of course, the hypothesis on N1, which would say for all N greater than or equal to N1, An minus L is less than epsilon over 2. And the hypothesis on N2 says for all N greater than N2, Bn minus M is less than epsilon over 2. Okay, so now what?
Specialized
Joe.
One.
And 1 to little n and
It's
F1. F1. This makes HN1 equal to what hypothesis? John. Perfect. Okay, and now we specialize hn2 to the same n with f2. That gives us hn2 that bn minus L is less than epsilon over 2. Now what? Go ahead, Jeffrey.
Triangle inequality.
The triangle inequality, we're almost up to the point where we can get the triangle inequality. We haven't used the fact that C is A plus B.
This is first add.
Yeah, we're going to add the two of them. So our goal is still that C minus L plus M is less than epsilon. So let's specialize HC to C, to N. Yeah. Specialize HC to N, so that HC now says, not for any N, but for this particular N, Cn is equal to AN plus BN. Brandon, question?
Is it hn to bn minus n? No, bn minus l.
Thank you very much. Thank you. Lean doesn't make that mistake. Humans do. Joe? Okay, I like it. So let's say have F3, which is the fact. Well, first of all, should we rewrite this this Cn into the goal? Because the goal right now, remember the goal still, we haven't done anything to the goal. It says, well, we did. We introduced n and this hypothesis on little n, but now the goal looks like this. So it still says Cn. Let's get rid of that Cn. So rewrite what? HC at the goal. That will make the goal AN plus BN. Yeah, so the new goal is that the absolute value of AN plus BN minus L plus M is less than epsilon. Does that make sense? So what's F3? Go ahead, Joe. You want to do something new?
Yeah. You just add the two inequalities, right? So AN minus L plus BN minus M is less than F.
Yes, in order to get there, I have to first rearrange things and then apply the triangle inequality. So let's rearrange things a little bit. AN plus BN minus L plus M is actually the same thing as AN minus L plus BN minus M. Why is that true? Ring. Okay, and then so let's rewrite this. Rewrite F3. I mean, our natural language proof is turning into a formal proof. It's just easier to communicate what you're trying to say formally if you have that language. This really feels to me, I think I said this before, I don't remember if I said this to you guys. This really feels to me like doing algebra before we had variables. Have you ever tried to read algebra from the 16th, 17th century? You take a thing and you square it and you subtract twice the same thing and then take that whole thing and divide it by 2. And I claimed that would be the same, like just write x squared plus 2x by, divide it. God, it's awful if you don't have access to variables to be able to compress that information. This is what it feels like to me to work informally. It's just so much, you can compress so much more information when you work formally. Even working, as you see, we're not using a computer at all. We're just describing what we're doing and keeping track of what's happening. Okay, we wrote F3. What's the new goal? Exactly, yeah. So we've grouped this and we've grouped that. Beautiful. Now we can have F4. What do we want to do with that absolute value of AN minus L plus absolute value of BN, same N minus M? Triangle inequality. Okay, that's less than or equal to AN minus L plus BN minus M. Why? Yeah, apply abs add. When you take the absolute value of things and then you add on the inside, that's the triangle inequality. Okay, so now this is our goal. Our goal is to show that it's less than epsilon. We know that it's less than this plus this. We know that this is less than epsilon over 2. We know that that's less than epsilon over 2. Linear arithmetic. Linearith. What facts do we need to feed into it? How about F4? We're certainly going to need F4. We're also going to need, what is this? HN1 and HN2? HN1 and HN2. And that's it. Let's do it. Let's see if it works. Any questions on the proof? Make sense? Let's do it. Let's see. How do I do this? Boom. And I guess I did that too fast. Okay, hang on a second. I want you to go away and I want you to go away. What do you mean crashed? What does crashed mean? Let's just try. Help. Apply. Okay, good. Okay, we're back. All right, so let's go back to the beginning of the proof. What's the beginning of the proof? Let epsilon be given and assume epsilon's positive. What's that? Intro epsilon, H epsilon. Beautiful. Okay, where are we going to get that? We're supposed to use epsilon over 2, so let's get that epsilon over 2. So let's we called it H epsilon 2, which is the fact that epsilon over 2 is also positive, and the proof for that is bound, something like that. Great, we have that fact. Now what? Specialize, let's specialize HA. Specialize HA to epsilon over 2 together with the proof that epsilon over 2 is positive. HA now says, where is it here? There exists some n. N is a dummy variable. We get to name it whatever we want to name it. Let's do the same thing for HB. Specialize HB to epsilon over 2 with the hypothesis that epsilon over 2 is positive. Great. Now what? We're up to this point in the proof. We choose N1 and HN1 using what? HA. And similarly, we choose N2, HN2 using HB. Now we've got these N1 and N2. It's asking for a capital N. What should we use? The max would be the right thing to use. I don't want to learn. I don't want to have to, we need more names of things. We don't need it. Use N1 plus N2. Yeah, let's be lazy. Okay, now what? Our current goal is for all n greater than or equal to N1 plus N2. Intro. Give me an n, give me the fact that it's greater than whatever. The goal has become that Cn minus L plus M is less than epsilon. Okay, so that n was given. Let's record F1 and F2. Have F1 is that N1 is less than or equal to N. That's by bound. Easy. Have F2, which is also the fact that N2 is less than or equal to N, also by bound. So far, so good. All right. And then we have this HC. HC says for all n, C of n is equal to AN plus BN. But now we have a little n. So let's specialize to that little n. Suhas. Sure, yeah, let's specialize HN1 also and HN2. Yep, let's do that first. I want to keep the formal proof exactly as our natural language proof. Thank you. Specialize HN1 to n, and I need a proof that n is greater than n1. I'm looking right here. That's F1. And similarly, specialize HN2 to the same n, but now with F2 as the proof. Now we're at the point, now we're up to this point in the proof. Specialize HN to C. Specialize HC to N. I'm so dyslexic. Okay, so now we know that that's what Cn is. You'll notice that I write the correct things, but say the opposite of what I mean often. Sorry. We'll get through it together. Now what? Rewrite HC. Okay, rewrite HC. Beautiful. Now we have the parentheses in the wrong way, A plus Bn minus L plus M. So let's get the parentheses in the right way. That's have F3, namely that AN plus BN minus L plus M is the same thing as AN minus L plus BN minus M, and the proof is that it is ring. Okay, that's a ring operation, and then let's rewrite by F3. rewrite by F3. Okay, now we have an minus L plus bn minus m is less than epsilon. We also know that an minus L is less than epsilon over 2. We know that bn minus m is less than epsilon over 2. We're in good shape. All we need to do is break this, and so that's F4. Have F4 is the fact that this big absolute value, copy, lazy, is less than or equal to the same thing, except with absolute values here, and that's because of abs add. Boom. Now it's just linearith. We don't even have to, we can't rewrite this. It's not an equality. So it's just linearith. Linear arithmetic using F4, the hypothesis on N1, the hypothesis on N2, and that's the level. Cool? You like this way of doing things? Okay, we're going to keep this. Good. Let's see how much farther we can get. I have to teach you a few more things. We're going to learn the split ands tactic. So how do you deal with ands and ors? This caret means and the opposite caret means or. If you ever forget, think of the and as the same as the intersection. Exactly. So think of this thing is and, so is intersection. To be in the intersection of two sets, you have to be in both sets. Okay, so this is and, whereas this one is or. Okay, that's why I don't draw greatest handwriting, especially when I don't use this thing that I brought and I try to do it with the trackpad. Okay, so our goal is to prove two things, that x is equal to 2 and that y is equal to 3. Our two hypotheses are that x is equal to 2 and that y is equal to 3. Okay, how are you supposed to prove two things? You split them up into individual things. That tactic is called split ands. Okay, so I write split ands, and it splits up. Look at what happened, Daniel. I don't think so, but I'll humor both of us. Linearith, if you feed it hx and hy, no, because it's not linear arithmetic. It's a combination of two things. There is a one. I don't want to teach you the one line version of this. I want you to learn split ands. Split up. We have multiple things. If the goal is an and, then you have to prove both the left side and the right side. So just split them up into prove them individually. That's split ands. Now look at what happened. There's an active goal, which is the one we're currently working on, but there's also a goal 2, which is the one we're not currently working on. Okay, so you can have 20 sub-goals. The complicated theorem will get broken up into a mess of sub-goals, but you work on them one at a time. So our goal used to be that x is equal to 2 and y is equal to 3. Now we have two goals. One is that x equals 2. The other one is that y is equal to 3. Okay, so you split up the ands. Sadvik? Exactly right. The object and assumptions are the same. I don't know what you mean by shared. When I do things here and I change the assumptions and I change the objects and I prove this goal, nothing happens to goal 2. They're not shared. If that's what you mean by shared, yeah. There's a split. There's a complete split in the logic, and now you do whatever you want to these objects, and the goal 2 sits in the background. Nothing's happening to it, unless you want something to happen to it. But we're not going to talk about that. Damon.
If you have an and assumption, split ands at that assumption, we'll keep it together.
We're going to have to do all those separately. We had a 2x2 matrix for intro versus there exists for existential universal quantifiers. There's an intro versus specialize and a choose versus use. There's going to be a 2x2 matrix for and or. So I'll get to that. I'll get to what you do when there's an and in a hypothesis. Joe.
If you solve one goal, do you use the result in solving the second one?
In actual lean, yes. In the game, I don't think there's a way to do that. The game only takes one line. The way you would do it in actual lean is you would have a have, which is basically the statement of the proof of goal 1, and you prove it. And then when you get to goal 1, you just say apply that proof. And then when you get to goal 2, you still have that as one of the assumptions. You can't do that in the game server because it'll only take one line at a time. But we shouldn't hit something complicated enough that you would need to do that. The better thing to do, if you want to split ands at the last moment. If there are things that you would do to both sides, then keep going and don't split ands until you're ready to change the logic, so that you don't have to waste time redoing logic you already did. that make sense? Sean?
How does it look in like the code editor?
In the code editor, very good question. In the code editor, what you'll see, I'm struggling with, oh, this isn't really how it looks in Lean. It's telling me that this is how it looks in the code editor. How it looks in Lean is that you see multiple goal states, the whole game board. There's one, and then there's another one, and there's a third one if there's more. Yeah. Okay. Let's go. So how do you solve x equals 2? Apply hx. And that goal is done. The intermediate goal is solved, and it automatically says, hey, you're not done yet. You have a new active goal, and the active goal is that y is equal to 3. Apply hy. Okay, that makes sense? Easy but simple. Let's go. What if you have an or in the goal? So now our goal is to prove either x equals 3 or y equals 3. Our assumptions are that x equals 2, and another assumption is that y equals 3. So how are we going to prove that x equals 3 or y equals 3?
Right.
The right one is the one that's true, and the left one's not true. Or we don't, to prove an or, you only have to prove one of them. So you say which one you want to prove. In this case, we want to prove the right one, not the left one. So I say right, and Lean says, okay, so forget about this x equals 3 thing. Can you prove that y equals 3? Apply hy. Okay, so if you have an or in the goal, it's left or right, depending on which one you want to prove. If you have an and in the goal, you split them up. Suhas.
What if like in the problem, there's like different cases where one is right, or the other is right?
Okay, that's the next level. The next level is, that's the level after the next level. The next level is, what if you have a pair of assumptions, an and in an assumption? So you have a hypothesis H that x is equal to 2 and y is equal to 3, and your goal is just that y equals 3. How do you get this second part of it out? And the answer is dot notation. Suhas, you want to say that? So h dot 1 is the fact that x is equal to 2, and h dot 2 is the fact that y is equal to 3. That's all. So what should I write? Apply h dot 2. And we're done. Okay. So dot notation says, give me the first thing or the second thing if I already have them as assumptions. And finally, let's get to Suhas's question. There's a tactic called cases, but the way cases works is not how I want it to work. So there's another tactic called cases prime. And unfortunately, that's the one that has the good syntax for us. Again, if you forget how it works, you just click up here, and it's cases prime on a so if you have a hypothesis, let's read this for a second. If you have a hypothesis H, which is P or Q, and I don't know which one is true, but regardless of which one is true, I can prove something. So if you have a hypothesis that either P or Q is true, you say cases prime H with H1 being the name for the hypothesis on the left side, and H2, you can name them H and H. You don't have to change the names. I find it useful. So you'll get two game boards. One game board has a new hypothesis, which is H1, namely P, and the other game board has the hypothesis that's Q. Okay, so that's a way of splitting according to which case it is. Does that answer your question, Suhas? So let's go. How do you do this? So we know that either x is equal to 2 or y is equal to 3, and we have to prove that x minus 2 times y minus 3 is equal to 0. Sean? Cases prime H with H1, H2. Okay, which is it? One of these things is true. I don't know which one. I don't have a way of proving which one, but in either case, I should be able to solve the goal. So when we did this cases prime H with H1, H2, H1 is now we know that x is equal to 2. And we want to prove this. We also have a second goal. The second goal is we know H2 that y is equal to 3, and we're trying to prove this. Okay, Suhas?
I don't know like if this is weird, but is there like this and or both of them can be true, right? So is there some kind of weird scenario where there's like if either of them is true, it works, but if both of them are true, it doesn't work, or something weird like that?
Like an XOR?
Yeah.
There could be, well, you would need an extra hypothesis for that, because this notation is not That's like for sets, you want the thing that's in one or the other, but not both.
Yeah.
That's like the set difference.
Yeah.
So you can cook that as x is equal to 2 or y is equal to 3, and it's not true that x is equal to 2 and y is equal to 3. You can cook that up. And then all the logical, you already have all the logic tools. These are the fundamental logic tools, and more complicated things can be built up from these. So you don't need new tactics. The 4 things that you have learned, cases prime, split, ands, dot notation, dot 1, dot 2, and left and right. Those are the 4 things that you need to handle any logic involving ands and ors. Does that make sense? Okay, so here we are. How do you solve this, Sean? Or do you have a question?
I had a question.
Please.
So, ors and ands would also have their own order of operations, right? Like, we have to watch out for that too.
You can always hover. Basically, it should be in the order that it appears. So unless there's parentheses. Yeah. I'll give you a homework assignment with all the distribution laws and easy stuff to work through, like De Morph laws. Okay, so we know that x is equal to 2. That's hypothesis H1. So Sean, let's rewrite H1 into the goal. And now we're trying to prove this. Ring. Okay, the intermediate goal is solved. We're not done because there's a second goal. Our active goal has become the second goal. We have the assumption that y is equal to 3. Rewrite H2 and ring. So far, so good? The original assumption was an or, and cases said, give me the case that x is equal to 2. So now we have that as an assumption with a secondary goal about what happens when y is equal to 3. So in either case, x minus 2 times y minus 3 is equal to 0 for different reasons with different proofs. How does
regular keys?
it works the same way, but its syntax is multi-line, and let me not even go into it. You need these let me not even go into it. I keep saying let me not, and then I want to go into it. So I'm cutting myself off, Joe.
If, like, you have an or statement and the cases in the proof for one being true and the other being false is a different case than both of them being true.
Yeah, so first you split on one or the other is true, and then later you choose whether to go left or right. You'll see. You'll just get a bunch of experience with this. Okay? Brendan.
I guess if we're like writing this, like doing like the formal like write up, I guess if it's like split into goals, like how, I guess, do we just like, I guess we can just write like the different assumptions and that's good.
Yeah, we'll if this is well designed, which I hope it is, we will soon see examples where we need this in an actual context, and you'll see exactly how to write everything that you need. Okay? It's good. We're making great progress. Okay, so here's our cheat sheet. Here's our 2x2 matrix. If you have an and or an or, if you have it at a goal or a hypothesis, if the and is in the goal, then it's split ands, and you have multiple sub-goals. If it's in a hypothesis and you want to access either one side or the other, it's h.1, h.2, dot notation. If you have an or that's in a goal, you have to decide which one do you want to prove. Do you want to prove the left one? Do you want to prove the right one? And if you have an or and a hypothesis, you break that up with cases prime with H, or using, is it using or with? I always get it confused. It's with. This one's with. Okay, here's our goal. This is a real goal, so let's actually work on it. Like so, and like, nope, here, like so. Okay, let me write down what's going on. Theorem. This theorem doesn't have a name because it's not important enough to have a name. The theorem says, assume we have a sequence A is given. Assume that sequence is given, and as is real number L. Okay, so we have a sequence, we have a real number. Assume further, moreover, moreover, assume, and I'll give this the name HA, that AN goes to L. And the claim, the goal, is to show that there exists an N so that for all N greater than N, AN, no absolute values, is at least L minus 1. So let's think about what's actually going on here. We have some sequence, blah, 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 some dots. It's getting closer and closer to L. And we want to show that eventually, for all N sufficiently large, above some absolute bound, you will never go below L minus 1. There's some point after which you will never go below L minus 1. How are we supposed to find such a point? Suhas sees it. Let me, can we make this a quiz? No, this is too hard. It's not that hard. I'll give you something else for a quiz. Daniel. Set epsilon, yeah, so the idea is set epsilon equal to 1, and then we have to be able to do something. Now, let me just say there's a new tool, and the new tool is AbsLe. And AbsLe is this theorem. It's a theorem that absolute value of x is less than y if and only if two things are true, x is less than y and x is greater than negative y. So let me just record that here. New tool is a theorem called Abs_LT. And Abs_LT says x is less than y if and only if two things, x is less than y and negative y is less than x. Okay, does that make sense? Does that make sense? If you're in absolute value, you're less than y if you are less than y as an upper bound and you're lower bound by negative y. So you're between y and negative y. That's what it means to be less than absolute value. Jeffrey.
Just curious, what happens if you put y less some negative value?
Right. So if y is a negative value, then this can never hold.
Oh, yeah.
So you don't actually, it doesn't need any axioms. It applies in any additive group with a linear order, with a additive left monoid. Yeah, blah, blah. You don't need to do anything to it, but we'll be a little careful about how. So this is a theorem, so we want to rewrite by this theorem. It's something that happens if and only if. Okay, the usage is to rewrite by this theorem. Okay, so that was the little aside. And let's go back. So we have this new tool. The idea is to set epsilon equals 1. Okay, so let's try to realize that idea. So this hypothesis HA, I guess let me make it a little, yeah. The hypothesis HA is that we do have A going to L. So continuing the proof, what do we want to do? Sean. Exactly. Specialize HA. HA starts with for all epsilon greater than 0, set epsilon equal to 1, and then we need a little stupid have F0 or something, is that 0 is less than 1 as real numbers. And that's by norm num or something, by norm num. Okay, so I'm going to need to feed this F0 into this specialization. Then HA will be what? There exists an N, so that for all N greater than N, absolute value of AN minus L is less than 1. Okay, so far so good. So now what? So we know that there's some value of N, so that beyond that value, the distance from AN to L is at most 1. This width is at most 1. Sean sees what to do. Jeffrey sees what to do. Oh, don't tell me. blanking. I'm on.
We choose that.
Yes, exactly. Let's take that n. That is exactly the n that we want. Because being within one of L in particular implies that you're no smaller than L minus one. Okay, so choose that exact n, NHN, using HA. Okay, so now we have that n. So choose n using HA. So we have that n.
Use that.
Use n, yeah. Use n. Jeffrey, I assume that's what you were going to say too. Yeah. Okay, so new goal state. The new goal at this point is what? Go ahead, Akil.
For all. Yeah. And then it's greater than equal to all of them.
Perfect. Okay, everybody see that? So what's our next line? Intro, yeah. So let little n be given and assume that, let's call this Hn, that n is greater than n. Okay. Joe? Specialize, exactly. Specialize H capital N. H capital N, what does H capital N say? For all little n greater than n, an minus L is less than 1. Right? It's just this part of the choose. Everybody following along? This makes sense? You just can't see? Is that better? Specialize Hn to what? Little n, and now I need a proof that n is greater than n. That's exactly H little n. So now Hn says what? I need to break this into two things. Which two things? Well, how do I break it? What is it? AbsLe, exactly. So rewrite, here's our new fact, AbsLe at Hn. So AbsLe is going to look for either the left or the right-hand side. In fact, it's going to look for the left-hand side. It's going to look for an inequality. Where's AbsLe? Right here. Good, we can see them both. It's going to look for this shape. Do I have an absolute value less than y? It finds an absolute value and a less than sign. So this thing is going to be x and 1 is going to be y. And the new hn, the new hn will be what? Other than Sean, other than Joe, other than John, Sam.
A of n minus L less than 1 or negative 1 is less than a of n minus L.
It's not an or, because to be within L in absolute value, you have to be sandwiched between L and epsilon and minus epsilon. And it's an and. This is really important. And an, or it's not an minus L, but rather -1, because they prefer less than signs. -1 is less than an minus L. Okay. What's our goal again? We introed n and hn. So our goal, by the way, our goal is what? Is an is at least L minus 1. Which of these, is it the left side or the right side of hn? Is it the first thing or the second thing of hn that will solve our goal? The second thing. The second thing, if I add L to both sides, says that an is at least L minus 1. In fact, strictly, and our goal is less than or equal to, but that can be solved. That's just part of linearith. It's linear, it's still linear arithmetic. If all I have to do is add both sides, add L to both sides and convert a strict inequality, like if I had to prove a strict inequality and I had a less than or equals, I'd be in trouble. But I'm actually trying to prove less than or equals, and I have something stronger. I have a strict less than. So that's a linear. Daniel, if you could put that away, please. Remember, we turn them off and put them in our backpacks. So now the answer, the final solution is linearith with what goal? HN, I think, won't work. Dot 2 will work. Dot 2. Okay, we want the second part of HN, and that will solve this goal.
In the first step, can you also choose epsilon to be and you add the smaller than one? That also works.
That's true. You could choose a half, and this whole proof should go through. Yep. Yeah. So idea. Nothing particularly special about one. Nothing too special about one. I mean, we were asked about L minus 1. We could have, let's put it like this, could have chosen epsilon equals a half, which is at most 1, and it would have worked just fine. Something.
Why was it problematic if -1 less than equal to n or something? That would be a problem.
What I said was, if our goal was to prove a strict inequality, and what we had was less than or equals, that's not enough.
Yeah.
You want to know that x is strictly greater than y, but you know that x is greater than or equal to y. Well, you have to somehow show that x is not equal to y. But if you already know that x is strictly greater than y, and you're trying to prove x is greater than or equal to y, that follows automatically. And linearith will make that transition for you. Okay? Let's try to execute this proof in lean. So here we are. That's the theorem. We have the idea. That's the new tool. Okay, we're going to start right here. Have F0. So let me get rid of all of this and slide this over. Don't worry about it crashing. Apparently that's not a problem for some reason. Okay, so I'm just going to write the first thing. Have F0. Do you want to use something other than 1? Pi over 3? A half? Pi over 3 won't work. Pi over 4. Yeah. Let's use a half. Let's see. I have to make sure I cast this to the reals. Let's use a half just to, I don't know, by norm num. Okay, we're back. So we have this fact F0 is that a half is greater than 0. And now we're going to specialize HA to a half together with F0. So specialize HA to a half together with the proof that a half is greater than 0. HA is the fact that A goes to L, which starts with for all epsilon, as long as epsilon's positive, yada, yada. Okay, so now HA is turned into, there is some capital N, so that eventually we're within a half of L. So choose, we're up to here, choose capital N, H capital N using HA. Okay, we've got our capital N. We know that as long as little n is greater than capital N, we're within a half of L. Use that n. Use that n. Now we know that we want to prove that for all n greater than. This is one thing, by the way, on the exam I saw some people were confusing, at least their words in natural language were confusing what they were assuming and what they were trying to prove. Try to be very clear about this is my new goal now, as opposed to we now have. You can't say we now have for all n greater than n, a of n is greater than L minus 1. No, that's not what we're trying to prove. That's what we're trying to prove, not what we have. Okay, so this is what we're trying to prove. Next step, let little n be given and assume that, yeah, so intro n hn. Beautiful. Now we can specialize hn to little n hn. Specialize hn, because it wants a little n and it wants a proof that little n is greater than n, that's h little n. Now we know that a n minus L is less than a half. What do we want to do to that? Rewrite AbsLe. So let's rewrite AbsLe at HN. That's the new theorem. The new theorem takes an inequality. If you have an absolute value less than, it can convert that into the thing itself is, I guess it did it the other way around from what I wrote. It writes negative y is less than an minus L, and an minus L is less than y, where y is a half. Okay, so I need to fix, someone can put an issue there so that the doc string is correct. Doesn't matter, right? It goes on the other side. And now what? Now we're basically done. We proved more that an is at least L minus a half, not just L minus 1. So it'll be linearith where you feed it. If I feed it HN, I think this should break. This linearith is this is a new version of linearith, which is too smart. Let's retry that. That's not what I want. I want HN.1. If I give it HN.2, it should break. Thank you. It can't do it with HN.2, but it can, I hope, do it with HN.1. Okay. Any questions? Awesome. We're making great progress. Next level. This is where we can have a quiz. The squeeze theorem. We're ready for the squeeze theorem. Okay. I'm just going to write something to wake it up. You can't do apply to nothing, but writing something reminds it to wake up. Here's our situation. We have sequences A, B, and C. We have a real number L. We know that A goes to L. We know that C goes to L. We know that B is always lower bounded by A and B is always upper bounded by C. And we want to know that B goes to L. Okay. Let's make a little bit of progress into this and then I'll give you a little quiz. So slide this to the side and let's keep working. Do you like working on paper? Okay. So new theorem. This is the squeeze theorem. We're given sequences A, N, less than or equal to B, N, less than or equal to C, N. We're given that A, N goes to L. We're given that C, N goes to L. And our goal, those are our assumptions. Our goal is that B, N also goes to L. What's the why would this be true? What's the picture? Do you have a picture in mind? Stop it. Yeah, so it's not, we don't know that A is monotonic. So A could be going like, let's say this is A. Whatever A is doing is getting closer and closer to L. That's A. And we know that C, well, B is between A and C, so C is always greater than A. So C, whatever C is doing, has to stay above A. And it's also going to L. And then all we know about B, we know nothing about B other than it's squeezed between them. Whatever B is doing has to stay no higher than C, no lower than A. That's B. Why is it the case that B then has to go to L? Okay, step one, Daniel.
Oh, we're absolutely good now.
What did you want to ask a question?
No,
Did you have a comment?
I don't. No.
Okay. So step one, proof. What's step one? Our goal is to prove seq-lim. Seq-lim is actually for all epsilon. So our first step is let epsilon be given. Yeah, intro. Let epsilon be given. Okay. Now what? What are you going to do with that epsilon? We need to find an n. Yeah, new goal. The new goal is there exists an n so that once you're past that n, bn minus L is less than epsilon. John. Very interesting. Epsilon and not epsilon over 2 or something. Very good. Very good. Eventually, an will be within epsilon over L from below. Eventually, Cn will be within epsilon of L from above. And B is going to be sandwiched between those two. So we don't actually need an epsilon over 2 or anything like that. It's enough to use epsilon itself. Very good. So specialize. What's the hypothesis? A to L. A to L. I guess I didn't. This hypothesis is called A to L. This hypothesis is called C to L. This hypothesis is called ALEB. A less than or equal to B. This hypothesis is called B less than or equal to C. Okay, and this is our goal. So specialize A to L to what epsilon? The epsilon that we have, and I need a proof that it's positive, H epsilon. Okay, and we'll call this hypothesis H epsilon. Specialize A to L to that, and similarly specialize not B, but C. C goes to L, epsilon, H epsilon. So the new A to L says there exists some n1, so that for all n greater than n1, an minus L is less than epsilon. And C to L, the new C to L, says there exists some n2, so that for all n greater than n2. Now, lean isn't going to automatically make the dummy variables have new names. It'll keep them dummy names, but I want to, for our purposes, keep different names. Now what? Yeah, of course, we have to choose n1, h n1 using A to L, and choose n2 and hn2 using C to L. Okay, so now this bit becomes hn1, this bit becomes hn2. Eeny, meeny, miny, mo. Daniel. Very good. What's the goal now? We're about to do the AbsLe. The goal is that there exists an n. Yeah, we would use the max or use n equals n1 plus n2. Okay, so now the goal says for all n greater than n1 plus n2, intro, n and hn. Okay. Now, is this the time for the quiz? I think it is the time for the quiz. Okay, so we're at this state. What is the current goal state? Tell me at this point, tell me every hypothesis, every assumption, every object. What does the goal state look like right now? That's the quiz. What's the current goal state?
Wait, just the goal state or like
The goal is just the goal, and the goal state is all of the information, the objects, the assumptions, and the goal. It's like the game board. I want to know where all the pieces are. There's a number of assumptions. There's not as many as it might seem. Let's make sure that we're keeping track of everything that's going on.
See that.
What's that?
Like set form.
You're tracing it back from the beginning? All right.
Are we allowed to use like N1 and N2? Because I think technically when you specialize like that, then this doesn't play.
We gave them names. We chose them.
So when you say use N equal to plus N2 or?
Yeah, this is natural language. So really, we would just say use N1 plus N2, but we're thinking of this as, that's what we're thinking of as begin. I didn't think this would be as time consuming. Trying not to be. Is there so many things?
Yeah.
There's not really that many, is there?
There's like the stuff that's left over from before.
But it gets destroyed. When you choose, A to L is gone. C to L is gone.
Oh, thank you.
What's that?
Oh, right, yeah.
You do have to write HN1. It's on the board already. Let's do it together to make sure we have time to actually solve this goal. Let's do it together. You want some more time? Okay, 1 more minute.
What?
You're gonna agree it's yourself, right?
What's the matter?
It's an opportunity for you to pause for a second and think about. Let's see if we can come up with it together. What objects do we have floating around? ABC are sequences, ABC are sequences, N to R. We've got the real number L. What else do we have? We have an epsilon. We have an N1 and an N2 that are natural numbers. We have little n that's a natural number. Anything else? We've got epsilon, we've got capital N, capital N2, we've got little n. Okay, what are the assumptions? HN1 says this, for all n greater than N1, AN minus L is less than epsilon. HN2 says for all n greater than N2, CN minus L is less than epsilon. That's it. And there's NH epsilon. You're absolutely right. That we already used. And ALE, that's right. You're absolutely right. A less than or equal to B is still there for all n. AN is less than BN, and BLEC is for all n. BN is less than or equal to CN. And HN. Thank you. I guess this isn't as simple as I thought. All right. N is greater than or equal to N. Thank you. Thank you. It's not it's not N, it's N1 plus N2. Okay, I'm going to give myself about a 0.25 on this one. And what's the goal? Absolute value of Bn minus L is less than epsilon. Sorry, that's not the goal. We introed an epsilon and we used N1 plus N2. So
Oh, wait, no.
intro N and HN, that is the goal. Okay, that's where we are. Very good. All right, give yourself a 1 and hand it over to, I think it is actually, it's a very good exercise. Yeah. Yeah. I don't care about subscript.
Oh, I think I will.
Please put your name on it.
Yeah, so
Please put your name on
I
it.
know we learned Sean.
Okay, we're almost there. So what's the next step? Yes, exactly. Okay, so let's have F1 is that N1 is less than or equal to N by bound, and have F2 that N2 is less than N by bound. Okay, then we can, thank you. Then we can specialize. Specialize what? HN1 to little n F1, specialize HN2 to little n F2. And now what? Yes, exactly. Rewrite AbsLe, abs less than. We want to do this at the goal. We also want to do this at HN1, and we also want to do this at HN2. We can do it in 3 steps, or we can do it at HN1, HN2, and at the goal. The goal is \goal,
Oh, that's cool.
the turnstile. Okay, that's just, you could rewrite it 3 times. You could write 3 rewrites. 1 for the goal, 1 at H1, 1 at HN2. Okay, so now everything is turned into HN1, the new HN1 says what? It says that negative epsilon is less than AN minus L, and AN minus L is less than epsilon. The new HN2 says negative epsilon is less than CN minus L, and CN minus L is less than epsilon. And our new goal is that negative epsilon is less than Bn minus L, and Bn minus L is less than epsilon. Right. Together with, so we have ands in hypotheses, but we also have ands in the goal. So we're going to want to split ands. Before we split ands, let's make sure we've done everything that we can so that we don't have to do more later. Joe? Exactly. So let's specialize. What is it? A less than or equal to B at N. And similarly specialize B less than or equal to C at N. So we have those inequalities. So now we know this says that AN is less than or equal to BN. This says that BN is less than or equal to CN. And now we're almost done. So now we would want to, split ands. And now we'll have one goal is this. Why is this true? So sub-goal 1 is the left-hand side. Why is that true? And yeah, and A less than or equal to B. That'll close sub-goal 1. And sub-goal 2 is linearith HN2 dot 2. The fact that C is less than L plus epsilon will tell us that B is less than L plus epsilon, because C is an upper bound for B. Together with B less than C. Less than C. Daniel.
You can just skip the split and the straight everything slightly in one.
It shouldn't, but it might be, yeah, the new linearith has gotten stronger. I have to like go in and manually temper its strength so that it's doing pedagogically what I wanted to. Okay, let's do it. Let's solve the squeeze theorem. What is? Oh, what is sorry? What is declaration use sorry? Sorry is the way to, if you don't know how to prove something, but you want to postpone it. We can't do it in the game. But in real lean, when you can have a have and you don't want to waste your time with the proof of it right now, but you don't want to get error messages. You just say, sorry, and I'll come back and prove it later. Okay, let's go. We can do this. We got 3 minutes, but we already know the proof, so we just have to write it down. Intro, epsilon h epsilon. Tell me the next line. Specialize A to L, epsilon h epsilon. Specialize C also goes to L, epsilon h epsilon. Beautiful. Choose N1, HN1 using A to L. Choose N2, HN2 using C to L. Use N1 plus N2. So where are we? We're here. Intro, NHN. Have F1, which is that N1 is less than or equal to N by bound. Have F2, which is that N2 is less than or equal to N by bound. Okay. Specialize HN1 to N together with F1. Specialize HN2 to also same little n, but now using F2. Beautiful. We got all these inequalities. Now, oh, let's check. I meant to check our goal state against the real goal state. Anyway, I think we got it right. It's, I guess we can scroll up before we did the halves. So right here. Did we get it right? A, B, and C, we got L, we got epsilon, we got N1 and N2. Oh, but intro, right? So here. And we introed little n. We've got A less than or equal to B, B less than or equal to C. Epsilon is positive, HN1, HN2, and HN. And that's the goal. Okay, so we got it right eventually. Very good. I think that's a really important exercise to be able to say, like, what is the global picture right now? Now what do? We rewrite AbsLe both at the goal. Do you know why LT and not LE? LT is less than, LE is less than or equal to. AbsLe, we want to do this at HN1, at HN2, and at \goal. And it does all three at once. Now we're at the point where we can specialize. Let's not forget to specialize what? A less than or equal to B to N, and specialize C, B less than or equal to C at N. And now we have A is less than or equal to N. Great, we have everything in place. Let's split the goals. Split ands. And why is this true? It's linear arithmetic using HN1.1. Let's just make sure. We have this lower bound on AN, but BN is even bigger. So that'll prove the lower bound that we need on BN. Everybody see that? And intermediate goal solved. Active next goal is the same thing, but now with an upper bound. So it's linear arithmetic with HN2.2 and the fact that B is less than or equal to C. And that's the squeeze theorem. All right.